When you speak, you have to come. Now it's okay. Camera is here, sir. He's on, but video is not coming. Yes, sir.
You are sitting on COVID. You sit there.
I'll just start it and then.
No. We do one thing. 1 minute. Hello, madam. Keep this chair here. 1 minute. Let this chair be here.
Am I audible? Hello?
Yes, sir. Can you start your video, sir?
Sir, you sit.
Okay. All right. Yeah. 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 Can you hear? Can you see me?
I can see you.
Shalekar. Hello.
Hi.
Thanks for joining us.
Not at all.
Ahead of time. Before you start the program. Huh?
I was told to join at 2:45.
Yeah. So 3 o'clock formally will start. Okay. Yeah. Coming in from where? You're at your home or?
Home. We have decided not to reopen the office at the end of this current
Not
lockdown.
yet. Okay.
Because we are not suffering working from home. Things are going on.
I know. That is true. That is right. Yeah.
Only one guy once in a while goes and checks the servers and all that.
Oh, okay, okay. Yeah.
Get together.
Chalo, madam, start karo.
All of you. On behalf of Director NAL, I welcome you all to the today Technology Day lecture. I request Dr. Vidyadhar Murkavi, Head CSIR 4PI, to introduce the chief guest and welcome him for today's lecture.
Yeah, thank you. And just mentioning, it's our first public event after the lockdown. And I'm thankful that, Dr. Sherlaker has agreed to be the speaker for the day. Just before I introduce him, just a couple of words about the event itself. And everybody knows that, the history behind the National Technology Day. We particularly, it's a moment of pride for CSIR because CSIR, one of the events, was very much the reason for celebrating the Technology Day. One of the prominent event was the Pokhran 2, of course, and which was done on the May 11th. And the other one was the test firing of Trishul missiles. And more importantly for us as members of CSIR, there is some disturbance. I think if others can mute. There is a lot of disturbance. I think if others can mute, I think it will be better. Yeah. So let me continue. So the other event, which is of course very close to our heart, is the flight of Hansa, which also occurred on the 11th of May, and that's an important event. And so we particularly take pride in celebrating the Technology Day. And I'm very happy that Dr. Sherlaker actually accepted at a very short notice. And we are trying out the new technology of being able to host this event through the electronic media, and I hope people will actually take benefit of that one. And just to introduce my friend, Dr. Sherlaker, he's my friend because I've known him for quite a while now, and we have often met essentially for a variety of reasons, starting the interaction when he was actually with the TCS. Dr. Sherlaker, of course, has a BTech in electrical engineering and MTech in computer science and engineering, and a PhD all from IIT Bombay. And then, of course, he also was at IIT Bombay as an adjunct professor. And then also for the ACSIR. He was the associate editor of IEEE transactions and on the steering committees of the ASPDAC and International Conference on VLSI Design and the Executive Committee of India Semiconductor Association. But I came to know him more in his capacity when he was working at the Tata CRL, Computational Research Lab, which was responsible for setting up then 134 teraflop system, which was called the ECA system. And it actually stood in at number 4 in the world at that point in time. And it was completely funded by a private agency. And we had actually gone and taken a look at that one. And there are a lot of interactions actually started with TCS and NAL, even including the many of the computations we did for the aircraft programs long back. After that, actually, Dr. Sherlaker joined Intel. And later on, he started a company called Sankhya Sutra Labs, Private Limited, which is incubated in the JN Center. Essentially, it's a company focused on the scientific computing with an initial emphasis on the CFD. It has a lot of promises. In fact, we also interacted with his company with a view to understand how it can be used for many of the complex fluid dynamical flows over aircraft. And I'm quite sure, while we are not yet reached the maturity in that area, I'm quite sure under the leadership of Dr. Sherlekar, we can do so. And the other aspect of Dr. Sherlekar is anything, he always, calls me and says, look, there's something like this happening which is very useful to India. And that is something which is very close to his heart. For example, I remember, him being the associated with the technology mission of Indian Railways. He had a lot of, interest in using the composites for the Indian Railways, making them more efficient. And we keep interacting on such issues. And he's highly technology-oriented person. And I don't think we could have found anybody better than him to speak on the occasion. And he has chosen an important topic today: simulation, role of computers, and of course the how we can actually benefit from the crisis. Sometimes the crisis can lead to more innovations. We look forward to hearing from him, and I wish to thank Dr. Sherlekar for coming and joining us. Thank you very much, Dr. Sherlekar. Welcome, and you may please start your talk.
Okay, so let me first begin by thanking NAL and 4PI in general, and my friend Dr. Mutkavi in particular. And it's always been great fun and a lot of very interesting interacting with him on all kinds of matters and talking freely and without any agenda. So it's been a good long journey from the time we knew each other first. Now, the only casualty of having a short notice is that I have not been unfortunately able to make slides. So what I am planning to do is I have notes on my screen, and I will use those notes to make my presentation. So you will have to just listen carefully to what I say rather than. Okay, actually, I can try and share the screen. Let me see how that works. Just a minute. Okay, so you can see the screen, but don't pay too much attention in reading it. Just listen to what I'm saying. So I will not talk about fluid dynamics or what my company does in this talk, because I think there are too many people who know fluid dynamics much more than I do in the audience. So I thought I'll play it safe and talk about other things. So what we will talk about is, you have this pandemic going on, and I'm sorry to begin with this because though whatever you read, anywhere you read, it's only about pandemics. So everybody must be actually sick and tired of it, but it's okay. Just bear with me. So we'll talk about emerging opportunities for computational sciences in this context. Okay, so let's start. During the pandemic, one of the things that has happened with computational sciences, though not necessarily high performance computing, is that there are softwares being developed for predicting the progression and regression of the disease. Okay, and this has been done by several institutes, not only in India but all over the world. But looks like one of the good ones is from JNCSR, IIT Bombay, and IISc. Three professors got together, and with a number of young volunteers, they developed a piece of software which was sponsored, and this project was sort of sponsored by the principal scientific advisor. Now, the interesting thing about this software is that it predicts the progression and regression of the disease at the granularity of a district. Now, this is important because, when you talk about how many cases are there of this disease, in India, that number doesn't really make sense because, I mean, India is of the size of Europe. So if you want to have information about the progression or regression of this disease, you must have it at the level of granularity where you can actually use that information and take action. So the district level makes sense. If it can be smaller, it will be even better, but at least at the district level. This software has a very friendly user interface. It works on laptops, it works on mobiles, and it accesses a web portal to give you all the information that you need. It's available publicly and is being used by government and others for planning of resources. Now, the computational aspect in this comes from modeling this process of the progression or regression of the disease. And this modeling is done in a sort of innovative manner, which is different from the way it is normally done. There are several models which are used in the world for doing this prediction, but this is novel in many ways, and it has managed to match the observations from various countries in the world, and so it is being used. Now, let's see. So basically, the idea is that since it is publicly available, uh, everybody can plan their resources depending on this prediction. So you know that so many people are likely to get infected. You know from the characteristic of the disease that out of these so many people will need to be hospitalized and so on and so forth. So from all this data, you can actually plan your resources as a hospital, as a quarantine center, as people who will supply equipment and medicines to all these places and so on. Okay. But the basic computational aspect is captured in a set of nonlinear differential equations, but these differential equations are all ODEs, and therefore their solution does not require really any high performance computing. Now, let me come to the post-pandemic scenario, because I mean, this thing is useful for the pandemic, but later on, it will be nice if we can leverage this understanding and this experience to do something which is useful beyond the pandemic also. So one of the things that can be done is you can create a healthcare management portal. So instead of this portal being useful only for this particular disease, you can create a portal which is useful in general for managing healthcare across the country. Now, here, the first thing that is required is data collection. You need data from all hospitals, all clinics, all pharmacies about what are the kind of diseases that are being treated, what is the kind of equipment that is being used for treatment, what is the kind of medication that is being used, what are the other consumables that are used in hospitals, etc., etc. So basically, that data collection is the first aspect that has to be put in place. Once that is in place, then you can provide access to a B2B electronic marketplace, online marketplace. Okay. Now, there is a company in Bangalore which actually runs a B2B marketplace, similar to Amazon, but Amazon is B2C, whereas this is B2B. These marketplaces can actually now do data analytics. So that is where now slowly computational sciences, mainly data sciences, and perhaps higher amounts of computing power, maybe amounting to high performance computing, comes into the picture. So marketplaces can do data analytics, including using machine learning, for example, on the backend servers to predict the demand on various time scales. Okay. Now, this is important because if you can predict the demand at various time scales, then people who produce those goods can also plan schedules so that those goods are available at the right time, at the right place. Uh, when you say various time scales, let us look at different time scales. So if you look at vitamins and food supplements, or you look at medicines for lifestyle diseases, then these are nearly independent of time. Okay, somebody who has to take food supplements has to take them throughout the year. Somebody who has to take medication for diabetes has to take that medication throughout the year. So there is really no major fluctuation in demand. But you look at another time scale, which is seasonal variations. So when you look at seasonal variations, you have medications required for allergies, which can change with the level of pollen in the air. You need medication for waterborne diseases, which typically show a spike during monsoon. And then you can look at long-term variations. For example, if there is an aging population, then you know that diseases such as diabetes or hypertension are likely to grow in the long term, and therefore the demand for such medications is likely to grow in the long term. Now, during pandemics, this marketplace and others can also access the prediction data from the forecasting portal. And therefore, the spike in demand that will be there because of the pandemic, that spike in demand can also be forecast, and appropriate step up in the manufacturing can take place. Now, individual hospitals, clinics, and pharmacies can also do their own data analytics for their own planning purposes in terms of their inventories, etc. And that is that is a form of what is commonly now called edge computing, where when you say edge computing, what we are saying is that all the data analytics is not necessarily done in a big way at a remote server. It can also be done in a localized fashion for a particular region, for example, okay, or even a particular hospital, for example. Now, they can also, the other thing is that if you create a database like this and have open access, then each hospital, for example, can also access the data of other hospitals, and this particular common access can be used by hospitals to borrow medicines and equipment from one another. Not only borrow, but share. A lot of equipment is extremely expensive, and if several hospitals in a particular region can get together and forecast their demand for the usage of such equipment, then that would reduce the cost that is incurred by individual hospitals. Now, having looked at these, which are essentially in the domain of healthcare, of course, I must mention that there are standard applications of high performance computing to healthcare, which are well known. So there is not much to talk about. Basically, in drug design, but in drug design, there is a lot of computational biology involved, and a lot of it is still in progress. For example, if you really want to simulate the effect of a new drug molecule completely in silico, then you would not only need to be able to computationally do protein folding, you will have to do it in a dynamic manner, because the way a protein, which basically what an antibody is, it attacks the virus, it goes and clamps around it. So unless you can do dynamic protein folding, you're not really there. And dynamic protein folding is really far away, because protein folding itself is not a done deal. Okay, so now let's look at other possible applications which are of a similar nature. One is a further generalization of this portal, a B2B portal for healthcare, which is to create a management portal for general retail business. Okay, now if you want to do that, so what you're trying to do is to optimally manage the entire what is called distribution system from the manufacturer of food items all the way to the consumer. Okay, so now here, especially if there are electronic transactions happening, then it is possible to collect this data from the smallest of kirana stores, starting from large retail establishment down to the smallest kirana stores. Now, if this data can be collected, then you can do a similar backend data analytics to figure out what are the requirements of various kinds of food items and how they change over time, over a season, over a month, over a week, and so on and so forth. And this data can be dynamically passed on to the producers, those who grow vegetables, those who grow grain, those who grow fruits, and they can then actually optimally plan their production so that it properly matches the forecasted demand. See, today one of the largest problems in the largest problems that farmers face is that they don't know what the demand will be in the future, and therefore they have to use some kind of a gut feel to figure out how much to grow of what. And that is why you see these wild fluctuations in the demand of vegetables, for example, because sometime the price of tomatoes are shooting through the roof and the whole bunch of farmers start planting tomatoes, and then there's a glut, and then most of them can't be sold. So basically the farmer loses whether there is a shortage of production or whether there is an excess of production. Now, if you put all these systems in place, then it will be possible through a forecasting mechanism for farmers to plan their production. And that will really alleviate a lot of farm distress. And as you can see, this requires a lot of data analytics in the background, so that at different time scales you can essentially forecast the demand and make it available to the producers. Now the time scales of course are different, as you know, for vegetables, for milk, for fruits, and for grain. The demand also changes. In summer the demand for milk, for example, is higher than the demand in winter. Now let's look at something else. Let's look at a similar management portal for the railways. Okay, so let's concentrate on one aspect of railways, which is to monitor the health of the rolling stock. Okay, now what does it mean by monitoring the health of the rolling stock? And just remember that when you do that, now we are talking about using not only data analytics but also using physics of the problem. And depending on what you are trying to solve, you will either use physics or you will use data analytics, or perhaps both. So now let's look at what is meant by let's say a healthcare system for rolling stock of the railways. When I say rolling stock, it means wagons as well as engines. So one of the ways, so just remember that when in India a passenger train comes to a terminal station like Bangalore, for example, then it takes several hours for the train with all its coaches and engine to actually take on another journey. And the reason why it takes several hours is because after it reaches the terminal station, it has to undergo a thorough check of all the components and subsystems to make sure that it is safe for another journey. Now, if you look at railway passenger systems in Japan, for example, if you take the bullet train system, when that bullet train reaches a terminal like Tokyo, it leaves in the other direction for another journey. It leaves in exactly 12 minutes. Okay? So all that needs to be done after it reaches a particular station is for the crew to change, for the passengers to get off, for the train to be cleaned, and for a new crew to get in and new set of passengers to get in. And this whole process is done very efficiently, so it takes only 12 minutes. The reason the train can leave in 12 minutes is because you don't have to check any of the components or subsystems in the train, because you are sure that they are all safe. Why are we sure that they are all safe? Because they are permanently being monitored all the time using a whole bunch of sensors. Okay. So the whole idea is that if you want a good turnaround time for your expensive rolling stock, then you need to implant as many sensors as necessary in every wagon and in the engine. Now, what would these sensors do? First of all, they'll keep track of the sensors. I mean, once you have the sensor input, what you do is you have a kind of IoT gateway on each train, and that train will take inputs from the sensors and continuously process those inputs to figure out if there is likely to be a catastrophic event such as a derailment. Now, if that is detected, then you have to take immediate action. So this processing has to be done very fast, and therefore it is done on the train itself. And this processing, so if there is a catastrophic event that is possible, then the driver has to be alerted. And in extreme cases, automatic brakes have to be applied. So this whole business consists of very sophisticated signal processing algorithms. However, there is more you can do now that you have this whole bunch of sensors. You can take all this sensor data and send it to the backend to a backend on a server. Now, what would the server do? The server would look at this sensor inputs, and at the server you may find that there are some problems with components and subsystems of the rolling stock. It's just that the problems were not severe enough to create a catastrophic event, and so the train was allowed to run. However, if those such problems are detected, then when the train reaches a terminal station, it will have to be sent. I mean, the appropriate wagons at least will have to be sent for maintenance. So now what is happening is you are not doing maintenance in a periodic manner. You are doing maintenance on demand. Now, not only is maintenance on demand, but basically it means that you have become far more efficient in the usage of your rolling stock, and your operating costs can go down, and even capital costs can go down very drastically. That's the second thing you can do. So basically, there's a lot of database activities, figure out what maintenance that needs to be done, which is the workshop that can do such maintenance, schedule maintenance in that particular workshop, send the wagon there, and so on and so forth. So that whole process can be automated. So finally, you can do data analytics on this sensor data on the server to find out if there is any component or subsystem which is failing too frequently. So through this data analytics you find that some component or subsystem is actually failing too frequently, it means that it is a good idea to look at redesign of the component and or redesign of the manufacturing process so as to improve the reliability of that component or the subsystem, so that it doesn't fail that frequently. So basically, this data analytics is an input to the design firm to check why this failure is occurring too often, and then it gets down into understanding the mechanics or electromechanics of that component or subsystem to figure out how to actually redesign the component or redesign the manufacturing process. Okay. Now, let's look at a similar problem with managing the modern power grid. Now, a power grid, a conventional power grid, the information flows one way from the consumer to the power station. Okay, so essentially, there's only one kind of information that flows, which is the frequency of the grid. And if the frequency of the grid starts dropping, it means power consumption is increasing. And if it is rising, it means the power consumption is decreasing. And accordingly, the power generation is managed at the power plants. Modern power grids are starting to have different kinds of problems because the power generation can now be distributed. That is one problem, which basically means there are windmills and there are solar plants and there are conventional power stations. Now, here the additional problem comes because the renewable energy sources such as wind and solar, they don't produce the same amount of power all the time. because it depends on the wind conditions and it depends on the sunlight that is available. So now, so whenever the availability from these two sources goes down, you have to crank up the conventional power plants like thermal power plants. Okay, and whenever the availability from this goes up, you'll have to reduce the power consumption in a thermal power plant. Now, there are two issues here. One is that you need to be able to predict how much by comes over a period of at least half an hour to 1 hour, because that is the time it takes for a conventional thermal power station to increase or decrease its power production. So you will need a good local weather forecasting tools which will forecast available sunlight and availability of wind, so that the power stations be told to increase or decrease their production. The other complication comes because conventional power stations also have their level of efficiency. So if you run them at lower than their rated capacity, then their efficiency goes down. So if you want to optimize the use of fuel such as coal or gas, then you will have to also worry about this matter. So basically, this is something which requires very sophisticated and accurate short-term weather prediction software. So which is directly into HPC. But you can also try to do some data analytics to find out how these things change over longer periods of time or seasonally, so that you can also plan how much of coal or gas to store in a power plant instead of playing it safe. Okay, so that is about power grid. And finally, I just want to make some comments about creating what is called a distributed economy. In the it's like a post-pandemic initiative. Uh, what we have seen is that a lot of problems in the cities. I mean, this pandemic is one, but for example, if you are living in Mumbai and if you have traveled by local train, then there is almost certainty that you are being exposed to TB. And the reason you don't get TB is because you have immunity. That's why everybody doesn't get TB. So the point is that these entire problems are due to excessive crowding in certain places. Now, if you want to sort out that problem, then one of the ways to tackle it is to basically industrialize the countryside. Now, that sounds like a funny idea, but we should remember that before the colonial period, Indian countryside was heavily industrialized. It's not as if everybody was dependent on farming. It's never possible. And that countryside got deindustrialized over a period of 200 years of colonial rule for various reasons. Now, the problem is to deindustrialize the country and appropriately distribute production. I mean, agriculture produce, of course, is in the countryside, but you properly distribute the production of manufactured goods in small towns and villages and in cities. So there are many things which require very high-end research and development, access to universities, and so on and so forth, which means that they have to be concentrated in cities. But a lot of manufacturing can actually be done in small towns and villages. Now, if you remember, Mahatma Gandhi was very keen on this village model, and Schumacher had written a book called Small is Beautiful. Some of you may know about it, which sort of articulated this idea of using the countryside. And then the other sort of, if you want, Nehruvian idea was to build large industries and large dams and so on. Now, there was a professor called Andrew Tannenbaum. I don't know if his books are still widely read, but if they are not, that's a pity, because those books are still very relevant. Those books were written in the early and mid 80s, and in those books, he had predicted every single aspect of the characteristics of today's internet and all the applications that run on the internet, uh, including net banking and so on and so forth. Okay, so he had that kind of a vision, and he had said that small is beautiful if the parts are in communication. So the idea is that you do a lot of simulation to figure out how to build the economy and how to distribute the production in villages, cities, and towns in an optimal fashion, so that overall there is economic prosperity. So of course, one can now start on the economy, one can start getting more ambitious and try to figure out what happens when you change certain policies. What will happen to the economy when you change certain policies? This is something which bugs every policymaker, and even the economists don't really know how to predict such things. So, uh, if somebody can create models for being able to predict such things, then those will be really useful, because computational power is available. What is not available to tackle such problems is the existence of these models. So that's all I have to say. Questions are welcome.
Anybody has any questions?
We can't ask any questions.
Dr. Shelekar, I have one question. Right. There are. I think this supply chain management is actually a very, probably well understood area or not a well understood area. Supply chain management, or is doesn't connect to the things that we do today, or is there a display? Yeah, can you just tell us about that?
Yeah, so supply chain management, see, any supply chain today also gets managed. I mean, after all, farmers produce vegetables and eventually the corner shop sells them to you. However, it is done in a very, very suboptimal fashion. And the reason is that everybody who's involved in the supply chain does not have access to information. Not only do they not have access, they don't even have access to current information. Forget access to forecasting of demand and things like that. So the only way to solve this problem is to use to use the internet, if you will, to create applications on top of it, which will collect data from everybody right down to the small shop, and aggregate this data, use data analytics to make predictions of demand, and make these predictions available to the producer. If and then, I mean, you have to make it available to the producer, to the person who manages logistics in terms of distribution, and everybody who's involved in this supply chain. And if you can do that, then the supply chain can become extremely efficient, and you can also reduce wastage, especially of food, in a very large way. And that is critical for the food security of the country.
So one of the things you are saying is basically the forecasting model is also has to be integral part of the supply chain management. That's one part of it. And second thing is the data. As regards to data, now the experience of, for example, the COVID-19 is that a lot of data that is now being put out actually is a crowdsourced data, basically. Right?
Yes.
Looks like most of it crowdsourced data, and I think looks like that is fairly authentic. And if you look at the correlation between the crowdsourced data from several countries, which are open, of course, and then and whatever is coming from the actual authorities, there is a fairly strong correlation, and then they track each other. Now, is that a good model for countries like India to be able
Yes.
to gather information? But
Yes.
eventually, I believe, at least I think it should go to the core. The data has to be in actually succeed. Your views on.
Yeah, so you see, when it comes to supply chain management, for example, for food, then gathering that data is actually not very difficult, especially in today's era of using electronic money, because every transaction is electronically logged. So when every transaction is electronically logged, all you need to do is to collect this information of log data, and that's what you need. So gathering data is not that difficult. And today this what you call this commitment to having formal transactions has increased because of GST. So because you can't get input credit unless you show a formal transaction, and once you show a formal transaction, the data is available electronically, and therefore it can be used to make all these forecasts.
Say something or shall I start? Yeah.
Okay, thanks. Thank you.
Okay. Yeah.
I am Jadhav, Director
Thanks
NL.
for calling me.
Any question? There won't be any question because you have muted everybody and it is getting into YouTube. So, but a large number of people are hearing you, and I must say first of all,
Okay.
with a very short notice, such an excellent speech you have given, and wonderful work you have done along with JNCR, IIT Mumbai, and IISc for such a wonderful portal which can give progression and regression of disease granularity up to district level. I must appreciate all the efforts of your team, sir, first of all. And also, we are taking a lot of message from your thing because, we also do a lot of prognostics and diagnostic thing in our aircraft, especially our structural monitoring and all other moving parts are getting monitored with a lot of sensors, and we call it as integrated vehicle health management system. So that system takes these all inputs from the sensors at various intervals. Some are at very high frequency data gathering, some are at low frequency data gathering. And then we put a prediction algorithm. We call it as prognostic diagnostic algorithm. More or less, it builds out on Bayesian theory on all that thing. And then uh, we are also have a challenges like aircraft when it lands, and the turnaround time should be less than 20 minutes, and such algorithms are most important for the maintenance staff. So I'm just remembering when you are talking about such a thing about the Japanese bullet train, the same thing we are also doing it in aircrafts at fighter and passenger aircrafts. So these are basically a very important issue you have touched today, and we will come back to you and take your help when we are developing such algorithms for our integrated vehicle health management system. So
It will be a pleasure to interact.
yeah, that is one part of it, and I was very amazed by you touch up to the distributed economy also, from healthcare management to distributed economy. And it was a very interesting lecture, sir, and we can correlate this with a lot of our aerospace related activities. Of course, my friend Dr. Vidyadhar has to do all this super computing in his place. So we are always doing two types of computing. One is make a quick computation on board and tell the maintenance people that aircraft is safe to take a next flight, and second one is offline. Okay, so that is how the our type of thing. And offline needs a huge computational power. Online doesn't need a huge computational power because online has been worked out with FMICA and FTA of that particular system. And as long as you are in that curve, we are clearing the aircraft. That's how it works. But offline is for the complete life prediction and all that thing, which takes time to do that. So this is how it is. And I once again thank you very much with such a short notice, giving an excellent lecture, and all our NL has benefited with your this technology day. Though it is on the it started with medical thing, but you already touched what we need. Thank you very much, sir, and thanks a lot. Once this pandemic restriction gets over, we will invite you to give a lecture on IVHM. Probably we can share you some details so that it will be useful for our engineers. Thank you very much.
I'll be happy. Yeah. Thanks for calling me.
Thank you very much, Dr. Shelekar. Thank you very much.
डॉक्टर मुत्कवी आप vote of thanks दे दीजिए so that we'll close it.
No, you have thanked me.
Formally.
Okay.
My pleasure. So yeah, in fact, like I mentioned to people that I have known Dr. Shelekar for a very long time, and for the first time when he started the initiative in the computational research lab, it was a mammoth effort, and he has been going at several directions at the same time, it looks like to me. And I think that is the perspective he has brought it today in the technology day lecture, because only then you can actually touch from one end of the spectrum of technology to the other end. But I think underlying all this, he has emphasized on the analytics, on the data science, and also not forgetting the physics-based models. And I think indeed the future does look like, it a combined modeling and simulation with data science coming in the very strongly, and being able to collect data, analyze data. We probably have a fairly formidable tool available to us to tackle a number of problems. And I think that is exactly the spirit of the talk that you have given. And thank you very much for that. And it has been a pleasure. We do hope that we'll have a physical interaction sooner than later. Thank you very much.
Thanks for calling me, and it was very good being able to say something in front of such an audience. It's a privilege. So I thank you too.
Thank you. See you, sir. See you.
Yeah. See you.